Okay, so this is the third session of this course topics in mirror symmetry and Ginzburg Landau model by John Alexander Cruz Morales from National University of Colombia. So thank you again, and let's continue.
Okay, so thanks, Marina. So and everybody for coming to today. So last time actually we were discussing the mirror symmetry of Fano manifolds, and we discussed that essentially the mirror of a Fano manifold, which admits some nice toric degeneration, is a Laurent polynomial, because we can see what happened using in one torus chart. And we actually asked if this Landau-Ginzburg, this Laurent polynomial, sorry, is unique. The answer was not, and I said that actually the different mirrors are related by some operation called mutation, and that's the topic of today. So I will try to introduce what mutations are, and I will focus on the case of surface, Fano del peso surfaces, because it's the well-known case. So in higher dimension, dimension 3 and higher, the situations are a bit more complicated and is less understood. But in dimension 2, in the surface case, I think it's kind of well understood what is going on with this mutation. So let me start with some notation for the definition. So let's consider x, y coordinates for the torus. This be the standard coordinates. Okay. Let's consider also B1 and B2. It's a vector. It's a primitive. It's integral. Primitive. Vector. Primitive here means that the greatest common divisor between B1 and B2 is 1. There, prime. Okay, so now we want to consider the following bidirectional map. So the bidirectional map, let me call it this mu B, torus, two-dimensional torus to two-dimensional torus. So given by the following thing, so we'll just say all these acts in the coordinates equal to x times 1 plus x b2 y minus b1 minus b1 comma y 1 plus x b2 y minus b1 minus b2. This is actually called a cluster transformation. So the cluster name comes from because this map is quite close to the map appearing in the cluster algebra theory. So that's what is cluster transformation. So I will say something about the relation with cluster algebras later. Also, some people call it this wall crossing map. It's similar map actually appeared in some paper by Arrow and studying some kind of wall crossing phenomenon. Right? So we want to use this map in order to define a mutation of all-around polynomial. I have to say that I didn't say that, but most of what I want to talk today is part of my old joint work with Sergei Galkin. So we actually introduce these ideas for the surface cases, but also there are work by other people. I will mention them during the lecture. Okay, so let's consider a Laurent polynomial. So let's W x y be a Laurent polynomial. It's a function of Laurent polynomial. So I want to define the mutation of this W. So the mutation of W in the direction of some vector U, in the direction of U, actually U, sorry, of B. So B again, here B is, as before, it's a primitive integral vector, right? Okay. How is the following thing? So we denote this by mu, the direction of B, W, okay? So the notation is given by the following formula. So I will apply this to the coordinates. So I will modify the coordinates according to the map mu before. You use W in the mu B x y, when actually this mu is this mu defined here, right? That's the mutation in the direction of B. So there is some important remarks. So in principle, this new, the mutation of W is not necessarily a Laurent polynomial. It's not necessarily a Laurent polynomial. It's a rational function, certainly, but a priori, there is no reason to consider that this is a Laurent polynomial again, right? That's the first thing. And the second remark is that actually the easiest way to compute this is still how to see how this mutation acts on monomials. So to mutate W, so we can replace each monomial of W by the following thing, by the following formula. So you have a monomial U1, Y, U2. So we replace by this U1, 1 plus X B squared B2, sorry, Y minus B1 minus U1 B1 minus U2 B2. Okay. So let's do it in kind of the easiest example. So you have for example, you have the example. So you get the wall crossing map or the cluster map. So the wall crossing map along 0, 1 is, for example, is to take the xy to this change of coordinates. This map will be kind of interesting. So we see before, and I will actually do. I will do another example. I mean, later in a second, which is more interesting actually. Good. So that's the thing. So we can take a Laurent polynomial. So we can apply this mutation, and we get another rational a rational function, right?
Mhm.
So we also can somehow mutate the vectors B. So we just mutate the Laurent polynomial, but we also can mutate the somehow these integral vectors. This is actually the tropical version of this map mu I defined before. So let me define this tropicalization. So let u some vector u1, u2, and b again b1, b2. Both of them are in C square. So the tropical mutation of u, tropical mutation. So actually again tropical, the name tropical comes from because this is actually related with kind of tropical geometry. So that's why the name tropical is in this mutation. So the tropical mutation of u, and because the map I will define is actually the tropicalization of the mu b before. So of u along b. So is the following from mu b u. So it's equal to u plus take the maximum between 0 and u1 b2 minus u2 b1, and we multiply this by b. This is also vector here, and that's the tropicalization of. So that's the mutation. So in fact, so again, a remark. This is the tropicalization. So this is the tropicalization of. So let me just put some name to this map here. So let me call it this asterisk. So it's actually the tropicalization of this map, provided that we need to change a little bit, use the one of the, provided one uses minus b b2 b1 instead of b2 b1 b1 b2. So that's the thing. So I will use these two maps. So I will use the map with mutate the polynomial, and the map we mutate actually the vector to define somehow the mutation of the Landau-Ginzburg model we want to do. So before actually doing this, I need to introduce some definitions. So a Landau-Ginzburg seat, Landau-Ginzburg seat. In the way, so if you look at my paper with Sergey, so you won't find this terminology. So this terminology actually came uh, after our work. It's actually introduced in the paper by Pascal and Tongana. So, but I think it's now more standard terminology. So that's but I am using this terminology, but it's not actually in my paper with Sergey, right? So what is a Landau-Ginzburg seat? So you have a Laurent polynomial and some collection of vectors. One, BK. Okay. So consists of a Laurent polynomial W of Laurent polynomial W. Actually, this is in two variables. So this W is So Laurent polynomial in two variables. Okay. So this is going for the surface case. And a collection of primitive vectors. Bi in C square. Okay. These vectors, the collection of vectors are called directions actually. We call directions. Right? And what is actually the thing? So the property this set should satisfy such that when actually take any of the mutations in this direction, so each mutation, so you take the mutation of W in any of these directions is also Laurent polynomial. So before I said that it's not, you mutate the Laurent polynomial, it's not necessarily a Laurent polynomial, but can be a Laurent polynomial. So when you have some Laurent polynomial and some set of directions in such a way that mutating in any of these directions, you get again a Laurent polynomial. This is called a Landau-Ginzburg seat, right? And then, so we can actually introduce the notion of the mutation of the seat, and the notion of the mutation of the seat is the following. So the mutation of the seat in the J direction is, so you mutate the polynomial with respect to the vector B, yeah, and then you need to mutate all of these vectors with respect to using the tropicalization B1, etc. So there is this in here, Bj minus 1. Of course, if you mutate it in the Bj in the direction Bj, you get minus Bj, etc. So mu. So what is the idea? So you mutate the polynomial with respect to the vector Bj, and you mutate all the vectors of the collection to get a new seed. So you get a seed with one Laurent polynomial and a set of vectors, right? So just to introduce the mutation,
Alex, may I ask you a question?
sorry.
Uh,
Sure.
I mean, I'm trying, there should be some, I mean, I'm trying to see geometrically what these mutations are. I mean, because we are thinking on Laurent polynomials, so we are thinking on meromorphic functions over something that we will see, I mean, so over an affine space. And then these mutations, what are they doing to, I mean, is there any geometrical way of, I mean, I'm trying to, from the
From
equation,
the,
from the form,
from the
I-
geometrical way, they are bidirectional maps.
just that. There is no other, okay, no other
No,
intuition, no
no.
symmetries,
That's somehow the geometric intuition that they accept. They're bidirectional
just
maps. So
just
they're just,
variational transformations. Okay.
yeah.
But
But this,
but
right. But at the
looks
end of the, but they're somehow in this context they have very particular property.
but
And somehow they should, I mean, for what we want to do here for the Laurent polynomial, for the mirror symmetry of Fano, we want actually that these marginal maps preserve the volume form.
okay,
They should have this property actually. But
okay.
I will talk about this uh, later today. But we
And
actually, for what we want, actually, they should preserve the volume form, the standard volume form for the tops.
Okay, and do
for
they
example.
come from some kind of generalization of inversion or whatever? Because they,
Maybe.
they, they
I'm
are
not sure.
very symmetrical in a way, and then I'm looking for
Yeah,
some more symmetry. So,
yeah. I'm not really sure, but right. I mean, you take for example, the mu, the inverse of this mu, right?
uh-huh.
I think that yeah, you take that will also, yeah. I mean, you can also work with the inverse actually. By the way, yes,
Okay, yeah,
and
because
you
of
can
the.
define everything with the inverse, right? Exactly. Yeah. Yes.
Oh, but, well, okay, thank you. Sorry for the interruption.
No, no, it's okay. So let me see what's going on. So okay, yeah, you said that we want to define the mutated um, set by this. This is the mutated set, right? The mutated. So let's do some example. Maybe this is kind of easily you look at example. So consider the following Laurent polynomial. So x plus y plus 1 xy. If you remember last time, we see that this is actually this is the mirror, the Laurent polynomial mirror to CP2, to the projected plane. You have this thing. That's the Laurent polynomial, and then consider the following uh, collection of vectors. In fact, this is not really an arbitrary collection. This one minus two one or one minus two. This is actually we can get it from using somehow the combinatorics to some kind of toric geometry or a polytope associated to this Laurent polynomial. But I will actually later say how to also how to get these mutation these directions actually probably in an easier way. But I mean this is not an arbitrary collection. That's what I say. You can get it from we can get this collection of vectors from some combinatorics coming from the Laurent polynomial. So we have these two things, right? So let's just mutate this. This is the Landau-Ginzburg sheet. So let's mutate it along. We choose one of the vectors. So vector 1 1, for example. So when you do that, we get the following. So we get this Laurent polynomial here, y plus x squared. You just apply the formula before, and then we have a new collection, which is -1 -1 -2 1 4 1. Okay, this is the thing, right? I will back to this, but there is something very interesting with in this example. So you can do it actually. I will do it later, but you can make the exercise that to mutate not in 1 1, but in the -2 1 and 1 -2. You see that you can get another Laurent polynomial, and then you get another collection, right? With this, what is this interesting in this example is the following. So you mutate this, and then you can start again. So you get this collection here. So you can mutate again and mutate again. So you can make the mutations. You can continue making the mutations, right? So you get now this polynomial, then you mutate again and mutate and mutate and mutate, and that is and you get a new Landau-Ginzburg seeds, right? And there is this interesting phenomenon you see. One other thing is like if you start mutated a Landau-Ginzburg seed, you get again a Landau-Ginzburg seed. that's something what happened in this situation. So if you mutate again and again and again, you get the Landau-Ginzburg seed. But there is also something interesting here is the following thing, that in this example, so the Landau-Ginzburg seeds in this example are in bijection, objective correspondence with the following thing. So with the solutions of Markov equations, Markov equation a squared b squared c squared equal to 3 a b c. This here a, b, and c are integers. This is interesting, and I also will back to this point later in a lecture today. So this is really interesting. So what does it mean? That you have a Markov triple, which is a solution of this thing. So you take a Markov triple, so to each Markov triple, A, B, and C. So we associate on our own polynomial. We can use W, A, B, C. So for example, for the solution 1, 1, 1, 1, 1, 1, so we have the Laurent polynomial x, y, x plus y plus 1 over x, y. And for the solution 1, 1, 2, so we get this Laurent polynomial. So this is really interesting that the Markov equation actually appears in this context. So maybe you know that Markov equation appears in many other contexts. In particular, for example, so if you consider the derived category of coherent sheaves of P2, right? And you consider, somehow the the mutations in the context of the exceptional collection. So there is also the combinatories of this is related to the Markov equation. So actually you can ask, if you know, for example, something about the theory of mutations in the context of the right category. So you can ask, what is the relationship between the mutations I am defining here and the mutations in the derived category setting? That's a kind of interesting question. I won't discuss it, but certainly using mirror symmetry, there should be some relation between them. And there is also, you want to control last time I defined the quantum differential equation for the Fanos. You define the quantum differential equation for P2. So you consider the Stokes matrices arising from irregular singularity. So the non-trivial entries of the Stokes matrix are also controlled by the Markov triples. So there is a lot of, interesting phenomena on CP2, at the mirror symmetry of CP2, the quantum cohomology, differential equation, etc., related with this Markov equation. And there is also, also in the theory of cluster algebras, Markov equation appears. So that's still interesting. Yeah. But we will see that in this, there is also another interesting relationship. And I will tell you this later. So the first thing is there is this theorem. This is theorem by myself and Galkin originally. But now there's mentioned by other people. We call it this is the Laurent phenomenon. The Laurent phenomenon for Landau-Ginzburg models. So what is this thing? So the theorem said that any mutation by Landau-Ginzburg and Landau-Ginzburg set is again a Landau-Ginzburg set, right? That's the thing. So if you mutate any of these Landau-Ginzburg sets, you get again a Landau-Ginzburg set. And what I said for the Landau, this is for Landau-Ginzburg models, right? So is the following thing. So let's go back to the example we have here for the CP2. So for the CP2, right? For the CP2, we have the following thing, right? So we get this polynomial. So let me call it this W, okay, 1, 1, 2, right? We call this polynomial. So you can ask, okay, what is the relation between CP2 and this Laurent polynomial 1, 1, 2, right? So the first observation I have to say is the following thing. So let me make this observation, which is important. So last time we defined what was called the period, the classical period for Laurent polynomial. So if you take the original Laurent polynomial x plus y plus 1 over x over y, so you can compute the period. So that's what we did last time in one example. So again, if you take this now this Laurent polynomial W1, 1, 2, this y plus x plus y squared over x y cubed, you can compute the period, right? So it turns out actually that the period, the classical period for the polynomial 1, 1, 1, p, which is actually x plus y plus 1 over x, is equal to the period of 1, 1, 2, p. Okay, this means actually the classical period, of x is y plus 1 over x is the same as the classical period of y plus x plus y squared x cubed. So they have the same period. But actually, last time we also established that the mirror symmetry between a Laurent polynomial and CP2, or in general Fano, could mean that the classical period is equal to the regularized quantum period of the Fano, right? So last time we proved, or we showed, or we discussed that the classical period for this polynomial here, x plus y plus 1 over x, is actually equal to the regularized period of the CP2. And that's the reason why this polynomial is mirrored. But now, because this new Laurent polynomial has the same period, this means that this polynomial is again a mirror of CP2. So that's what we have. So the conclusion is like this polynomial W 1, 1, 2, which is equal to y plus x plus y squared over x y cubed is also a mirror of P2, right? So what we're actually getting here is actually a collection of mirrors, because if we use the following thing, actually we can say it in the previous theorem. We said, okay, you have a Landau-Ginzburg seed. The Landau-Ginzburg seed is again, the mutation of the Landau-Ginzburg seed is again a Landau-Ginzburg seed, right? But now, if we start with a polynomial which is mirror to some Fano, in this case to CP2, so what we get actually is mirror again. So the Laurent polynomial we get actually a mirror to the Fano too. So in this particular example, what we have is that, so in fact, so we have a infinite collection of mirrors for CP2, actually controlled by the Markov triples. So in fact, any of these polynomials is a mirror of CP2, right? It will be, and this ABC is a Markov triple. It's a solution of the Markov equation, right? So for the moment, you just take into account, if you remember the last Folklore conjecture I said in the previous lecture, so that there was this kind of tonic degeneration associated you know, to any of these Laurent polynomials in some charts. So this actually suggests to you probably that, okay, that there should be probably some kind of relationship between some tonic degeneration of P2 and the Markov triples and the Landau-Ginzburg models, which are mirrored to P2. So actually, I will back to this point later. But okay, that's good. Perfect. But then let me say something which is important, but probably, I don't know, if you kind of related with Marina's question at the beginning, or it could be related. So you see, being a mirror means that the transformation, these mutations actually preserve the period, but preserving the period, so for the Laurent polynomial, means actually that we have some certain birational transformation preserving the volume form. That's the thing. So let me just remark that cluster transformations preserve the period of the one. Okay? And actually, these are the same birational transformations okay, that preserve the volume form, the standard volume form. This is really interesting because somehow in dimension two this is known. So somehow the Cremona group, the group of birational transformations of P2, is kind of relatively well understood, and in particular the birational transformation that preserve the volume form are actually well understood too. So let me just say this thing. So in dimension two, the subgroup of the group of birational transformations of P2 Cremona group that preserve the volume form is well understood. This is in part, thanks to the work of Blanc. So actually, Jeremy Blanc did the following. This actually was conjectured. It was conjectured by Usnik in his thesis, in his PhD thesis. They proved the following thing, that if you have the birational transformations of P2 preserving the volume form, this group actually generated by the group of automorphisms of this square. Some particular P. This P actually is just these mutations. So actually, remember the first map I defined here. So you maybe have to consider some change of coordinates, or maybe the another direction, but maybe -1 or something. You see, where is this? Is here, right? It's kind of kind of the inverse of something that is kind of related with this map here. So this is what actually called P, people call P the mutation. So the variational transformation that preserve, in the plane, that preserve the volume form are actually generated by this group, which is actually why not. This is kind of and this automorphism of the torus and this mutation, right? So that actually links the study of this Cremona group, which some people call this a special Cremona group because of that special Cremona group. So the study of the special Cremona group and the mirror symmetry for del peso surfaces, right? That's good. So there is this remarks using things. There is only one. So this actually means that we have these seeds, these Landau-Ginzburg seeds, and their mutations. So are some an instance of the general notion of cluster algebras. So there is only one difference, which is not really, at first it's not really trivial, is the following thing. So the difference is that in our context, so the difference is that in this context, in the context of Landau-Ginzburg models, context, the number of directions used for mutations is not necessarily not necessarily coincide with the numbers of variables. In fact, you see, we have more directions than variables in this example. So we have for example, in the surface case, we have only two variables and we have three directions for the CP2, for example. And we can get more and more directions if we go to other cases, right? And in the cluster variable, in the classical cluster variable, sorry, in the classical cluster algebra setting, this number should coincide. There is this, however, there is this word by Gross. Okay. So there is this word by Gross, hacking, and kill. So, for example, you can find it in their ICM talk on cluster algebras and bidirectional geometry. Maybe it's there. Cluster algebras and bidirectional geometry. So they proved that. So they explained that LG6 can be modeled or can model in the language of cluster algebras, classical cluster algebra, just adding additional variables, like introduction auxiliary variables. This is, somehow it is kind of folklore, you want, but honestly, I mean, even this is, being recorded, but I will say that for me, it's not that clear. I mean, I don't see actually how they do this. I mean, I talk sometimes with Mark and he explaining how to do it, but I don't understand very well how is this addition of variables or these auxiliary variables, possible in this context. So, well, right. But let's see that this is kind of accepted that we can get usual cluster algebra stuff using this approach, right? And that will be kind of in, interesting for you know for studying somehow the geometry behind the cluster algebras and also the cluster algebras approach to mirror symmetry to Del Peso surfaces, because this is the other thing I had to say that I just mentioned CP2 and I gave one Laurent polynomial and one set of directions, but for other Del Peso surfaces we have the same thing. So for other Del Peso surfaces, there is a list of Landau-Ginzburg. So I don't want to give the list here, but you can see the list in the paper by Pascal F and Tom Conan. You have this probably. The team Marina actually send you the paper in an email. So Pascal F and Tom Conan. So they have a list of the 10 the surfaces and the list. I will call it this PT list. And the list corresponding actually to the directions, right? So, for example, I just mentioned an interesting example is you take the blue up of 4 points of CP of P2. Remember that last time we said that this is M0 pi bar. This is a degree phi del peso surface, which is in this case actually the Riemann for compactification of the model space of genus 0 curves with y mark points. So you have the Laurent polynomial mirror to this will be given by this formula, for example, in this list. Right. This is W. And the collection of vectors are minus 1, 0. This times 2 means that you have twice minus 0, minus 1, 0 in the collection. You have also 0, the vectors 0, minus 1 twice. And you have 1, 0, 0, 1, 1, 1. These are the directions of the mutation for these double peso surfaces. And for the others, there are other cases, right? This is also interesting because this is an entoric case, right? This is an entoric del peso surface, right? Good. So in our work with Galkin, with Sergei, so we defined some object because we were actually motivated to the relationship of the cluster algebra. So we want to see if we can construct some cluster algebra out of this setting. So we couldn't actually find a cluster algebra, but we found something which is called the upper bound cluster algebra. So we define actually this object in our work, which actually package all the information about the Landau-Ginzburg seeds, right? So in my paper with Galkin, for example, so we define what we call so-called upper bound cluster algebra, okay, which is the following algebra. So the set of Laurent polynomials in two variables. Okay. Such that you have W and certain set of directions is a Landau-Ginzburg seed. So I package all the information about the Landau-Ginzburg seeds for a concrete polynomial, right? Which is what is interesting about this thing that this algebra it is relatively easy and or we expect to be easy, and this helps to understand the mirror picture for the peso surfaces. So there is this proposition. So actually it's written in Pascal F. Konkonov. But it's also again actually in this paper is a proposition. In my paper with Galkin, this is a conjecture. I will say why it's a conjecture. And it's the following thing. So actually, essentially what it says is that this upper bound is a kind of polynomial. It's a polynomial ring. That's what they say, okay? So the proposition says the following. So let take some collection of vectors, okay? But this is not arbitrary, so this is B1 of the 10 collections of vectors in this list. So what I say is that, okay, we have 10 del peso surfaces. So for any del peso surfaces, there is this list with the Landau-Ginzburg, the Laurent polynomial mirror, and also the vectors in the directions, right? So we call actually the exchange collections. So take one of these collections for actually any of these collections is the collection related with the mirror of one of the peso surfaces, okay? So if you take this, so what we say is that then this upper bound is just this polynomial algebra. And who is this W0, where actually W0 is the polynomial in the list, is the correspondent Laurent polynomial in the list. Good. So in other words, you take any polynomial in the cluster, in the upper bound, sorry, so has the form equal to F W0, where F is just a polynomial in one variable. In one variable. Okay. So somehow why was actually okay, if you want to sketch the proof of this thing, so the sketch actually is related with the theory of cluster varieties. I don't want to sketch the proof, but that's the thing. So somehow we couldn't find a very rigorous proof with Sergey, so we have some sketch. And if you go to the paper by Pascal and Tankana, so they said, okay, so this is a conjecture in the paper by these two guys. Yeah. And we talked with some experts, like Mark Gross and other people, and they said, okay, this is well known, this is kind of folklore. And Pascal and Tangano, they gave some sketch of the proof, which was essentially the sketch we know with Sergey. So for me, it's still a conjecture in the sense that there is some issues we need to fill some details, and we need to understand much better how actually the cluster varieties enter into this picture and what will be the cluster variety we get in the mirror in general for these surfaces. This is still, for me, not well understood, but probably, again, for other people, some experts like, Deniero or Mark Gross or Kiel, Konsevich, etc. So they said, okay, no, this is completely clear, and it's kind of an easy observation, probably, right? But still, looking at this in the details of this proof will help to understand how actually not just the cluster algebra, but also the cluster varieties enter into the picture, right? I don't want to discuss because I don't have time to do it this time, but okay. If you want, we can talk later about that and another what time. Good. That's important. Good. So this proposition is kind of interesting because give us somehow an idea that the mirror of the del peso surface is a kind of cluster variety. And we're gonna ask, okay, what happened in general? So we don't restrict to the peso surfaces, but we want to restrict we want to consider higher dimensional funnels. So let me say that we can actually define. So I will redefine the notion of mutation in a second in order to tell you that we can actually define mutations in general, in any arbitrary number of variables. So, and we can expect that actually the mutations defined that way actually preserve the period. So if you get a mirror, you can get again a mirror for the final surfaces. what is the problem is like in dimension, at least for us, I mean, at least for me, one of the problems is that in higher dimensions, we don't have a good structural understanding of the birational transformations of CPN. So somehow here in the dimension two, I try to explain to you that there is this close relationship between studying the special Cremona group and studying the mirror of CP of the Peso surfaces. So somehow the fact that we have this nice uh, description of the special Cremona group actually helps a lot to understand the mirror symmetry for the Peso surfaces. But if you go to dimension three and higher, so we don't have that good, description of the special Cremona group, in particular in dimension three. So that will be kind of interesting to study. And I have some work in progress with Eduardo Alves, trying to study this situation in dimension three and try to see how to extract information about this Cremona group for CP3 and how to understand microsymmetry for Fano trifolds in general, right? Well, but in any case, so we can have some definition for mutations, even if it's not exactly in the same way I did before. So let me do that. Let me try to introduce this thing. So there is this. You can find this in these two papers. There are two papers probably. So one paper by Coates and Kaschik. Beaton and Dayton. This is okay. So the paper is maximally mutable Laurent polynomials. And you can also find it in this paper by Kaschik and Prijalkowski. Okay, the paper is Laurent polynomials in mirror symmetry. Why and how? So in this paper, you find the following definition for the mutations. So let me write the definition. So let's consider the following. So let n be a lattice of n. Before we have a lattice of rank 2, right? Now we have a lattice of rank n, right? And take an element in the dual lattice. So M, which is the dual lattice, comes between M and Z, a primitive element. Okay, in the dual lattice. In the dual lattice. Okay, so consider this thing, omega perp section to n, which is the set of all vectors in n, such that omega, so WB is equal to 0. Okay, and consider a polynomial, Laurent polynomial. Polynomial. So Laurent polynomial. Polynomial. Somehow in the zero graded piece. Graded piece of this here. So this is because this omega, so this W per this W actually induce a gradient, in the ring of Cn. So good. So this, but okay, so we have a Laurent polynomial. So we have this pair. So we have the pair given by this element in the dual lattice and this polynomial, right? So this pair defines an automorphism of this ring via the following formula. So let me call it mu, because there will be the mutation. So this depend of this WF. So automorphism is the rational function, not just the polynomials, rational. And take the xb to x to the b f wb. That would be okay. So we say the following. So we say that if you take a polynomial f, Laurent polynomial f, Laurent polynomial f, smoothable with respect to this pair WF if you take the G is equal to this automorphism here applied to F is again a Laurent polynomial. And G is the mutation. G is called a mutation of F. Okay. And the people call this capital F a mutation factor. Usually this coincides with the definition we did in the dimension 2. Let me do the example. Let me do an example to see that this is what happened. Exactly what we have in the dimension 2, right? Stay with this f. X plus y plus 1 xy. So let me start with this. Good. So now I just rewrite this in different ways. So x plus y plus 1 over xy. This is equal to y 1 plus 1 y squared x plus x is equal to 1 over x 1 plus x squared 1 plus 1 and is equal to y 1 plus x 1. Right? So I did this because I want to coincide with my old computation. So if you look at the paper by Prichelkowski and Kapchik and Prichelkowski, so there is you have to interchange the value of x and y. That this means that you have to change some sign in the vector W, so it doesn't matter. So I did it this way to just to get this to fix with my own computation. So that you have these three ways to to see how to we can see this polynomial. So this means actually that there are so these are three different mutations of f. It actually should correspond to the three directions I have in my definition of the mutation. So let's see what is the thing. So let me start with the original Laron polynomial here. So I will do it with another color here. So with Y, for example. So we have this blue. You can see the blue. It's okay.
Yes,
Yes.
yes.
Okay. So we have this 1 plus 1 y square x. Right? This is one of the composition we get. So let me just take this also y 1 plus x y y, and then we have x y 1 plus x squared. So let's see that what is in the parentheses, this thing, let me do it with red, this will be df. So now let me just say, I will want to mutate this polynomial in y, so x plus y plus 1 x over y, but I will use this decomposition to get to mutate with vector 1 minus 2, and what will be the factor? So the factor will be this, the factor will be 1 plus x y squared. That will be the factor. And then we get the following polynomial here. So this is the first mutation, y plus x 1 plus 1 x y squared. So that's the mutation in the direction 1 minus 2. We use my previous formula, but here we use the same direction, but you also use the factor here that comes from this factor here. So now, in this case, so now we want to mutate with the direction 1, 1, and the factor will be 1 plus xy. And using the new definition, so we get y plus x squared. That was actually what I got in the first example. And then the last thing is like take minus 2, 1, the other direction, and the factor is this one. So the factor is, that will be the f. And then what you get is x is 1. Right? So this means that this is somehow the mutation of this polynomial here. The mutation of this polynomial here, the measure of CP2, by using any of these, the previous directions I defined. But now you also emphasize what will be the factor f here in the definition, right? What will be the factor f here in the definition, right? That's the thing. And then, so we have 3D equivalent results up to some monomial change of bases. So let me just mention all these mutations give equivalent results up to monomial change of basis. But we are actually, I just want to remember that there is some different, we use different mutations, right? If you remember the folklore conjecture I gave in the previous section, let me just go back to this folklore conjecture. So you have this folklore conjecture, remember? If X is a Fano variety and X admits a degeneration to a Goresten Fano-toric variety T, then the mugle of X admits a torus chart, right? Such that the Landau-Ginzburg mugle to straight to this Laurent polynomial. So this means that if you have a Fano manifold and you have a Laurent polynomial, so you mutate, what I'm saying that you mutate the Laurent polynomial. So this means using this picture here, this conjecture here, that you have the original Fano, so you have a toric degeneration. So you have a toric variety associated to this Laurent polynomial. So you have a toric variety associated to the mutation, right? That's good. So let's back again. Oh, sorry. Okay. So let's go back to here. So this means actually that for these mutations we did, so the corresponding toric variety T is equal to this projective plane, which is actually a Q-Goresten. This QG means Q-Goresten, right? Gorenstein. Deformation of P2. So what we see is that there is this change. So we start with P2 and its mirror, which is 1, 1, 1. So we get this degeneration here, this deformation here, which is P114. This is W1, 2, right? You see, right? 1 is 1, 1 square is 1, 1 square is 1, 2 square is 1. So you can continue and you see, for example, you get this 1, 4, 25, and this should correspond to this Landau-Ginzburg model with this another triple, Markov triple, and then again you can get here P 4, 25, 29 square, and then P 1, 25 square, and etc. etc. So you see, there is this relationship between the toric deformations of P2 and the Laurent polynomials, and what is actually what you get. So the values ABC in the Landau-Ginzburg model. So the values A, B, and C of the space, the degenerations P square, B square, C square. Okay. satisfies the Markov equation. So, and that's somehow the toric degenerations, the toric deformation of P2 are controlled by the Markov equation, are controlled by the mutations of the Landau-Ginzburg model. So, and actually this is so due to some result, to a result of hacking the Q-Goresten deformations, the generations of P2 are exactly this P square, B square, C square. So there is this relationship, and that's actually, according to somehow to the picture we have for the mu of CP2. So because all this line of this, so the mutation of the potential W111, all the mutation of this give us all this degeneration picture for, or this deformation picture for CP2. That's really interesting. So in fact, this is more, I remember, more general. So hacking proper obtain a similar result in the Picard one case, the Picard one. Yes. For surface. So this is really interesting, right? So, and there is a symplectic contrapart of this thing, you see, because remember, mirror symmetry is a relationship between symplectic geometry and complex geometry. There is also a symplectic approach to this, studying, some kind of exotic tori in P2. This is some result by Viana, belong some work by Aro. Also in Pascal F. Tonkanok, the motivation was the symplectic side of the story. So I won't actually talk about this thing, but there is kind of symplectic version of these mutations. The Landau-Ginzburg seeds, they call it some kind of Lagrangian or something seeds, something like that. So there is some symplectic geometry version of all this story, which is very, very, very interesting. And you can look at somehow you want to look at the symplectic version, so maybe symplectic version of this in the work by Viana, and also maybe um, Daniel. People. Okay. So, but I have 5 minutes probably, so I will just want to say something about how this fits in the mirror picture. So, questions of what does this look in general, like this, I did for CP2 in general, more general. So there is this conjecture that the mirror conjecture is the following. So let F and G be mirror partners to X. X is a Fano manifold, right? X is Fano. Okay. Then F and G are connected via a sequence of mutations. So you take two different mirrors, Landau-Ginzburg Laurent polynomials using this, approach we use that, you can look at the rhetoric chart. So then if you take two Laurent polynomials, it doesn't matter if they look two different or not, they should be related by a sequence of mutations. You have all the mirrors that should be connected by the mirror. So actually, one of my interpretation of this is like, if in the mirror side you get some kind of cluster variety, so these mutations, the way they are connected, the different mirrors are connected, that should give you some idea how these different torus charts should be actually glued together in order to get the cluster variety, right? Okay, but let me send another question. So again, so we have this Laurent polynomial should be, so they should be corrected by mutation, but the question will be what class of Laurent polynomials are mirrored to Fano? So the question is some conjecture by Coates and his collaborators. So rigid, the answer will be rigid, maximally mutable Laurent polynomials. Rigid, mutable, maximally mutable Laurent polynomials, right? So what means to be maximally mutable? So let me just say that a Laurent polynomial is maximally mutable if it admits, this is a kind of a rough definition, it admits as many mutations as possible. And one of these things, a maximally mutable Laurent polynomial is rigid if it is unique determined. Unique determined by mutations, by the mutation that he admits. Okay. By the mutations that it admits. There are more precise definitions. You can find in the papers by Coates and other people. That's good. So actually, let me just finish in the dimension two case. So in the dimension two case, essentially, in dimension two case, there is this theorem by Coates and other people that essentially what they say is the rigid, mutable, maximally mutable around polynomials, actually, are in correspondent into variables, and in one-to-one correspondence to the Q deformation, QG deformations, families of smooth del Peso surfaces. So for the list, this 10 list. So that's actually said somehow this conjecture is true in dimension two, right? I mean, you have only the rigid maximally mutable around polymers can come as a mirror for the Peso surfaces. There is some similar result for dimension three. You get the 105 families. The problem is that in higher dimensions, so we really need to care about terminal singularities, right? So we cannot avoid like what happened in dimension 2 and 3, the the singularities, because in dimension 2 and 3, these Gorestein terminal varieties with quotient singularities, they are smooth, but not in dimension 3, dimension 4 and higher. So this makes the picture a little bit more complicated. And again, so that's related also with the classification program I mentioned last time, because somehow you can rephrase the classification of Fano manifolds in terms of the classification of these Laurent polynomials. We have this property of being maximally mutable and also rigid. That will be somehow how to use mirror symmetry to classify Fano manifolds. So thanks. That's all for today.
Thank you, Alexander. Let me. What is here? Let me end the recording.